All the results that were previously obtained for continuous time random process can be easily extended to discrete time random processes. Starting with the notation, the continuous time argument t with parentheses is replaced by the discrete time instant n with square brackets. With respect to the statistical averages, the definitions of the mean and the autocorrelation are totally equivalent. The mean of a random process, now discrete time, is the expected value of the random process, and the autocorrelation function is the expected value of the product between the random process at a given discrete instant and the random process at another time instant. The time instants, in this case, are discrete time instants, for instance, n plus k and n. If we have a random process that is complex, in the definition of the autocorrelation, the random process in the second instant is complex conjugated, exactly like for continuous time random processes. The definitions of stationarity and cyclostationarity are also straightforward. A discrete time random process is stationary when the mean is constant, doesn't depend on the time argument, and the autocorrelation evaluated at two discrete instants with a separation k will depend only on this separation k. Similarly, two random processes are cyclostationary when both the mean and the autocorrelation depend now on the time argument, but the dependence is periodic. Periodic with a period n samples, now an integer period, but the same equivalent relationships. The power spectral density is obtained by means of the discrete time Fourier transform of the autocorrelation function if we have an stationary random process, or as the Fourier transform of the time average in one period of the autocorrelation function if we have a cyclostationary random process. Now the period is in an integer number of time instants. And the power can be obtained by integrating the power spectral density. The integral is now from minus pi to pi because we have the power spectral density of a discrete time sequence, and this power spectral density is periodic with period equal 2, and can also be obtained in the time domain by evaluating the autocorrelation at 0 for stationary random processes, or by evaluating the time average of the autocorrelation at 0 if we have a cyclostationary random process. Finally, we have the relationships between statistics at the input and at the output of a linear system. The mean of the output is equal to the mean of the input times the addition of all the coefficients of the input response of the linear system, or the mean of the input times the frequency response evaluated at omega equal to 0. The autocorrelation function is equal to the convolution of the autocorrelation function of the input with the input response of the system and the matched response of the system. This is equivalent to a convolution with the time ambiguity function of the impulse response of the system. The power spectral density at the output of a linear system is equal to the power spectral density of the input times the square modulus of the frequency response of the system, and the same relationships than for continuous time random processes also appear for the cross statistics. The cross correlation between the input and the output is equal to the convolution of the autocorrelation of the input with the matched response of the system. And the cross power density is equal to the power spectral density of the input times the complex conjugated frequency response of the system. All the results obtained for continuous time random processes can be easily extended for discrete time random processes.